So it's a great pleasure to invite you again for the beginning of the new semester. And our first talk in the semester is given by Vijay, and he's going to talk about his spectacular new work. And so over to Vijay, over to you.
Well, thank you very much for this invitation, Ayan, and thank you everybody for, I know it's in India, but now it'll be the evening, so thank you to everybody who took the time to show up. So today I'll tell you about some work we did a few months ago on the origin of black hole entropy. This work is done, the papers are here. The way this work is done in collaboration with Albion Lawrence, who's at Brandeis, Javier Magan, who is now an assistant professor at the Instituto Balsero in Bariloche, Argentina, and Martin Sacieta, who is currently a postdoc at Brandeis. Huge credit here to Javier and Martin. This work wouldn't happen without their insights and into this problem. So let me start out by, there's a little bit of a lag, by the way, in the slides. So if the slides have lagged for you and I've started talking ahead, just tell me so that I can sort of adjust appropriately. So, so today we're going to discuss a famous and important topic, the puzzle of black hole entropy. So let me remind you about what that puzzle is. So already in 1973, Bekenstein and Hawking, Bardeen, and Carter proposed that black holes carry an entropy that is proportional to the horizon area, and the proportionality constant is c cubed over 4g h bar, c being the speed of light, g being Newton constant, and h bar being Planck's constant. And we're going to set h bar and c equals to 1. Now, the really remarkable thing about this formula is it's completely universal. It appears to apply, or they proposed it applies, to black holes of any mass, angular momentum, charge, and space-time dimension. So it's as if it's completely universal fact about things that describe kind of warping space-time, gravitational theories in the low energy limit. Their arguments to arrive at this formula were as follows. It was basically Gedanken experiments, thought experiments being done with equations. And the way their arguments went was like this. So you ask yourself how black hole solutions in general relativity change when matter passes through the horizon. And they found that if you pass an amount of matter delta m, change in mass is delta m, then the area changes according to this formula. Delta m is equal to kappa delta A. In classical processes, delta A is always bigger than or equal to 0. And kappa, this proportionality constant, is the surface gravity and is constant across the surface, across the horizon. So these authors noted that these three equations are in formal analogy to the laws of thermodynamics, and thus proposed that maybe that there was an analogy there. But then at the end of one of the papers, I think the Hawking, Bardeen, Carter paper, there's also the comment that you shouldn't take this analogy too seriously, because if you took it seriously, you would need black holes to radiate with the temperature kappa. And they don't, they thought at the time. Well, a couple of years later, Hawking showed that if you include quantum mechanics in the background of a black hole, then you can do things like pair-produced particles just outside the horizon. One falls in, one goes out, and that produces Hawking radiation with precisely the right temperature, and thus the analogy is complete. Indeed, it would appear that black holes are like thermodynamic objects, and the horizon is a measure of the entropy. There's a more formal argument due to Gibbons and Hawking in 1978. So because we're going to use arguments like this, methods like this, I'm going to repeat that argument for you. So it's not just analogy, there's some calculation that says that, well, you should think about this as an entropy. So to remember that formal argument, it helps to first start with something without gravity, easier to understand, and to consider quantum field theory with some fields phi and some action I. And now let's consider the path integral in Euclidean signature. So we take t to I tau, and we make time periodic with the period beta. And let's see, if I do the path integral with these boundary conditions, because of the periodic boundary conditions, I'm computing a trace of e to the minus beta h. That's what the path integral computes. So here it is. I compute d for integral over the fields of e to the minus 1 over h bar times the integral of the action. So this quantity, by definition, is the partition sum. And Usually, and so if we choose to do this in the semi-classical limit, so we take h bar to 0, this is going to be dominated by saddle points. So in general, there's a sum over the allowed saddle points. But if there's one saddle point, you have e to the minus beta I times the fields evaluated on the saddle point of this theory, namely the solution, a solution to the equations of motion that satisfies the boundary condition. So given that we're now saying that the partition sum is e to the minus beta times I, we can identify I, the saddle point action with the free energy, and then the entropy is going to be beta dd beta minus 1 acting upon the free energy. So that's the standard formula we would normally write down in quantum field theory and that we learn in a statistical physics class. Gibbons and Hawking basically applied this idea to gravity. The way they did this is they said, take t to I tau, and identify tau with tau plus beta. Now, in gravity, you have to be a bit more careful than in field theory because you can't just do this because, you have to solve for the equations of the motion with these boundary conditions, even for the background geometry, not just for the quantum fields that are moving around. The geometry will change also. So, okay, so you analytically continue the geometry in effect. So, but let's see how that works. The action we're working with is like this. It's minus 1 over 16 pi g, Ricci scalar minus some cosmological constant. As usual, there'll be a boundary term. This is the extrinsic curvature at the boundary. As you know, you need the extrinsic curvature of the boundary in order to get well-defined equations of motion because the bulk action has a second derivative action, so you need this first derivative term on the boundary so the Euler-Lagrange variations are well-defined. And in addition, in some cases, you can add counter terms at the boundary built intrinsically out of the boundary metric, out of the intrinsic boundary metric to make this action finite. Sometimes that works and sometimes that doesn't. It depends upon the cosmological constant. Okay, so according to the instruction from our general idea of path integrals, we need to compute the saddle points of this action with these boundary conditions that you have periodic time. And the saddle point in question has this metric, and this is the metric of the Euclidean black hole. Okay, so the Euclidean black hole geometry is sometimes referred to as a cigar geometry, because Euclidean time goes this way. Actually, this circle is really an entire sphere, right? In d dimensions, there'll be some d minus 1 sphere, but I don't have the artistry to draw that, so we'll just draw it like it's two-dimensional. So you have Euclidean time going this way, it's periodic. And then if you just look at the spatial sections, they go this way, they shrink, and they shrink to a point here. So this is sometimes referred to as the cigar geometry. If I look at this geometry from the right-hand side, looking in like this, then this is going to look like a disk. Here's that disk. And this point at the origin is this point here, and that is the Euclidean horizon. And it's the horizon, it's the analytic continuation of the horizon, basically because if I continue this metric back to Lorentzian signature, we're going to find that the horizon basically develops out of the analytic continuation of this point. Anyhow, this is the saddle point. You can plug it into this action at the top of the page and then evaluate the action. If you evaluate the action, well, you get the free energy in the thermodynamic analogy. And then if you take beta dd beta minus 1 acting on that action, you get precisely A over 4G Newton, namely the entropy that Bekenstein, Bardeen, Carter, and Hawking had proposed. So that's a calculation, a formal calculation arguing that the area over 4G Newton should be thought of as an entropy. And I should say these pictures apply, as I've shown them, to vanishing and negative cosmological constant, flat and ADS space. So positive cosmological constant, de Sitter space, is a bit different. Since the Euclidean geometry actually has no boundary, it is a sphere, and so things are a little bit different in the way we've got to think about that, and what the meaning of its entropy is not entirely clear yet. So for this talk, I'm just going to avoid the case of positive cosmological constant. Okay.
Vijay, can I ask a question?
Absolutely, yeah.
So about the previous slide.
Yeah, I moved it back, but there's a lag.
So so when you're differentiating with respect to beta, so are you thinking of conical singularities there, because beta is fixed by the mass of the black hole if you demand smoothness? So how are you thinking about the derivative?
Yeah, so you're really asking how you smooth out this thing here. Well, You're asking when you take this derivative, what do you do with this action?
When you were thinking of the derivative with respect to beta, presumably you have in mind see, what I'm saying is that the smoothness determines beta in terms of the mass of the black hole completely. So this partial derivative here at a fixed mass wouldn't make sense unless you allow conical singularities at the tip of the cigar.
So you can do one of two things. You can, absolutely. So you can allow conical singularities and just simply do this derivative. You will get this answer. You can also try to smooth out that conical singularity by putting a little cap. Another thing you could do is you can sort of cut a little hole there, evaluate the action, and then you always have this little hole there. You evaluate the action, you differentiate. That is indeed what you're saying is one of the traditional doubts one might have about exactly what's being done here. And you'll recall that in a more modern or more recent context, there are similar doubts one develops about the argument by Aitor Lefkowitz and Juan Maldacena for the RT formula. You similarly get a conical defect. You make some argument that you can smooth that out and that class of regulators will not change the answer. But that is a doubt that is valid to have.
Okay, thank you.
Did that answer your question or not?
Yeah. So I presume that you could do like in their paper this calculation as well. That's what you were saying.
Yeah. So you would smooth it. So you would smooth it a little bit, and then do the calculation in that class of metrics, and then take their answer.
Thank you. But sorry, I'm not fully understood actually the difficulty here, because unlike this Maldacena-Lefkowitz calculation, here we can hold the temperature fixed, right? We can define the temperature by the length of the circle, and then simply compute the particle function based on it and differentiate it. It will be a function of.
So Gautam's point is that if you fix the temperature, then you will have a conical defect at the origin. And really the question is, what do you want to do with it? Do you want to say that there is an added contribution to the action from the conical defect because there's some defect term? Or do you want to say there isn't a contribution because, well, it's a very benign kind of defect? Or do you want to smooth it? And you can clearly make different choices for how you want to regulate it away from the saddle point where the mass and the temperature are related in the right way. So the assertion I'm trying to make is these various choices are give similar results, give the same result, and so we are okay with that.
Yeah,
and if you have a doubt about that,
if I just define this I in terms of the saddle point contribution alone, then there is no problem.
Well, you have to still differentiate with beta.
Okay.
Right. So basically, you have a circle, and it's a question of what you're holding fixed. If you want to hold the mass fixed in the metric and change the periodicity, so if you in this metric there's some mass term somewhere, right? There'll be a 1 plus gm over r kind of term. So if you hold this mass there fixed while changing the periodicity, you will have a conical defect.
Yes.
And really the question is, how do you regulate the contribution of that conical defect? Fair question. And so the assertion I'm making is choose some regulator that you feel happy with, which could vary from ignore it because it's a very mild singularity, or you smooth it in some way, you make a little hole, you can choose various kinds of approaches to dealing with that, and just declare that there's a boundary here and regulate that in some way. You will find that you will get area over 4G. That doesn't necessarily have to cure our doubts completely, but that is what you'd want to do. The kinds of things that I'm going to do in a little while are going to be using the Euclidean path integral. It's going to be more analogy with the Lefkowitz Maldacena setup, but still that is based upon this setup, and this is the moral origin of this kind of thinking. So that's why I mentioned.
Thanks a lot.
Okay, so by the way, thank you for the questions, and please keep asking them. Okay, so all right, so if there is actually an entropy, it behooves us to ask, what is its origin? And Gibbs and Boltzmann already more than 100 years ago taught us that if a system has an entropy, you should think about it as the logarithm of the number of microstates consistent with the macroscopic parameters. Now in quantum mechanics, it's a little bit more subtle than that, because you can take two microstates and take their linear combination, it's also a microstate. So it's a bit more precise to say that in quantum mechanics, it is the logarithm of the dimension of the underlying Hilbert space. So that's the object that's supposed to compute the entropy. Okay, so what approaches do we have in the theory of gravity to understand what appears to be an entropy for black holes? Well, so famously, one famous approach is the one due to Strominger and Vafa in 1996. And they gave an absolutely precise count of the microstates in string theory. They just counted them. They said, here are the charges, here are the macroscopic charges, the mass, the charge, etc. And let's just calculate how many microstates of string theory are consistent with this. And they got the answer, area over 4 G-Newton, beautiful result. But their computation was possible in certain special cases, which had lots of partially broken supersymmetry. In fact, the underlying theory had 32 supercharges, right? Enormous amounts of supersymmetry. It had extra dimensions, like string theories usually do. It had branes floating around, and basically both electric branes and electric charges and magnetic charges. Were there multiple electric and magnetic charges? All of this is to say, beautiful calculation as this is, this doesn't really look like the black holes that we see in our world, and as such, the computation has not been universal. If you told me, can you explain the entropy of a Schwarzschild black hole in this way? We might have a hard time doing that explanation in detail, just because there are so many special symmetries being used to do this calculation. That is not a critique. This is an extraordinarily beautiful paper. But it's true that to get an exact count in that way, we had to use many, many special properties of the particular theory under question. So in that sense, it's not universal. Another idea that people have pursued, especially pioneered by Samir Mathur, and more lately by Bena and Warner and others, is the notion of a fuzzball. So a fuzzball is a horizonless microstate geometry. Now, the idea of the fuzzball program, it's really the finite gravitational constant version of Strominger and Vafa. Let me put it like this. In Strominger and Vafa, to do this calculation, they had to take the coupling constant G string and send it to 0. And they were able to do this while preserving the degeneracy at each energy because of the supersymmetry, of the partially broken supersymmetry in the system. So because of that, they could guarantee the degeneracy of the system wasn't changing even when they were fiddling the coupling, unlike, for example, the hydrogen atom. So these folks, Samir and others, and Bain and Warren and others, basically wanted to do the calculations in the situation where G string is finite and not being sent to 0. And that limit, they tried to argue that you don't have a stack of D branes just, at one point that you're counting the states off, but rather you should think about the D branes as spreading out and making some kind of fuzzy structure that they called a fuzzball. And because they're looking at a pure microstate, it shouldn't even have a horizon. So these are their horizonless microstate geometries, and they have made progress towards this. But again, because this is a very hard problem, and in order to make progress, they need lots of supersymmetry and extra dimensions and other kinds of things for stability and control. There are many charges in the game, a little bit like Strominger and Vafa. And again, the argument does not feel universal. And the black holes in question don't look like the black holes in nature, partly because of the many charges and extra dimensions, etc. And perhaps the biggest challenge to date is that not enough such states have been identified in order to fully explain the entropy. Again, this is not a critique. This is an ambitious and very interesting program. But anyway, both these classic approaches have not so far been universal in their explanation of the properties of the black holes that we see. A third class of explanations that people have tried is to suppose that black hole entropy is somehow related to entanglement between the interior and exterior degrees of freedom. Now, I first saw this idea in a paper by Holgi, Larson, Wilczek in 1993, and then Susskind and Uglum had papers, and many people have written about this. Now, the problem with this class of approaches is that, at least in quantum field theory, this entanglement entropy between interior and exterior diverges because, well, the usual UV divergence of entanglement entropy in quantum field theory. And it's not actually completely clear how to compute this in string theory, where you might hope it would be finite, but it's not really clear how to compute it. Okay, so those are some classic approaches. Now, in today's talk, I would like to pose the puzzle in a different way. So far, I have been talking as if it's very hard to find these microstates. But actually, there's a sense in which it's very easy to find microstates. So I'm going to think about microstates that are semi-classical in the sense that they are microstates, but they can be described in some effective field theory coupled to matter with a fixed exterior geometry. So, I'm going to keep the exterior geometry fixed, and I'm going to ask myself, can I do other things in the interior? And there's a sense in which it's clearly obvious that there are many such states I can put in the interior. For example, there's lots of room inside. I can put a tennis ball inside the black hole, right? That's one state. I can put a tennis ball in a different location inside the black hole. I can put 2 tennis balls inside the black hole. And if you count up how many such effective field theory states there are that you could pack inside the black hole while keeping the exterior geometry fixed, actually, the effective field theory entropy computed this way is way bigger than area over 4G Newton. So from this point of view, our problem isn't that it's hard to find the states. The problem is that there appear to be vastly more such states than the Hilbert space dimension that is set by the by the black hole entropy. Right, so sometimes this kind of problem is this way of posing the problem is phrased in terms of Wheeler's bags of gold. So he referred to this kind of idea by saying, well, the black holes and other such geometries look as if there's some exterior region, there's some horizon, and then inside it there's this gigantic space. That's what he referred to as the bag of gold. And it feels like you can pack too many things inside that relative to the expectation from the entropy associated with this horizon. So we're going to take this attitude. Okay, you're going to say that there's a sense in which it's clear that there are too many states, and our real goal is to figure out why we have the exact right number of states, why these are not independent. So to repeat what I just said, here's our approach and our results. Our goal is like this. So the idea of this talk is going to be that we don't actually need to find a very specific family of microstates like Strominger and Waffa or the fuzzball program, right? It's not some very, very clever, hyper-specific family of microstates. It can be a very non-typical family of microstates.
One question. Yeah, I just have one question. Regarding this bag of gold, is it simply because entropy goes as area, and while we have a volume, degrees of freedom inside a volume?
It's even more than that.
I see.
It's even more than that. That is indeed partly the reason, but it's even more than that because it could have been that the interior volume was not actually that big. So in fact, the interior volume is both huge, exponentially big, and also growing rapidly in time. So it's a very serious problem from the point of view that there's a lot of space to pack things.
I see.
Okay, so as I was just saying, it's not that, so we would argue that it's not that you need to find a very specific family of typical microstates or particularly well-controlled microstates of that kind. We just need to show that whatever basis of microstates you choose to write down, right, and we can pick some highly atypical basis of states, right? We just need to show that they span a Hilbert space of the correct dimension, that is e to the e black hole entropy. That's our goal. Okay, so what's our approach going to be? So first, we're going to construct an infinite family of well-controlled semi-classical microstates. So I'm going to try to convince you that I can actually write down an infinite number of states that you would agree with me are reasonable-looking black hole microstates. And what's more, not only are they so reasonable that they even have semi-classical descriptions. In other words, there is a microstate there, but they're all, if I wanted to describe, take a coarse grain a bit and describe them semi-classically, it's a perfectly fine state of the kind that we're used to. That there's infinite families of these that keep the exterior geometry fixed. So then I'm going to construct from these states the gram matrix of overlaps. The gram matrix is a thing where, the diagonal entries are state I overlap state I, so like 1, and the off diagonal entries are like state 1 overlap state 2, state 1 overlap state 3. Basically all the overlaps. You construct a matrix out of this, and then what we're going to do is we're going to compute the rank of this matrix. And from linear algebra, the rank of this gram matrix is the Hilbert space dimension. So we're going to just basically calculate the Hilbert space dimension. And we're going to get the following results. The first result that I will show you is that the entropy, computed this way, basically the log of the Hilbert space dimension, is precisely area over 4g Newton. There are a couple of things that I would love to have time to tell you more about, and I probably won't, but you can ask me in questions. I'll have a slide each about this. One is the extension to flat space and collapsing geometries. We can argue that the same result will apply in flat space. That's why there's an argument here that this works for things that are coming, that look more like astrophysical black holes. And another very curious and interesting thing that will come out of this is that many of the geometries that we'll talk about will have long wormholes. So, if I look at an eternal black hole, for example, there's a wormhole behind the horizons. Many of these will have wormholes that are much longer than the usual wormholes. And we will argue our results imply that very long wormholes, super exponential wormholes, are a superposition of short wormholes. So this is, we would claim, a cosmic macroscopic manifestation of quantum mechanics, and that it's evident here that such things happen. So I'll spend most of my time on 1, and we'll spend little time with a slide each on 2 and 3. Any questions so far? I'm about to dive into the actual technical details of the talk.
Vijay, I have one very, maybe you are going to address this anyway. So how controlled is this calculation? Because how precisely if you know the ground metric, this receives some loop corrections or whatever.
Yeah. Could you ask that question again later? I will try to convince you that this is totally controlled. To add the question about loop corrections, there will be a paper coming out in the next couple of weeks by Roberto Emparan, Martin Sasieta, Alejandro, forgetting his last name, Villar, and Javier Magan, calculating loop corrections and showing that you get back the walled corrections and things of this kind.
Oh, okay.
Actually, they tell me there's also a paper possibly by Luca Eliesu and others doing similar, also doing that with supersymmetric black holes, but I haven't spoken to Luca, so I don't know if that's true. That was sort of secondhand information from things, but I do know about this other one. So that'll come out shortly. So hopefully directly addresses your question when it comes up.
Okay. All right.
Okay. So let me start with the technical details. So we're going to first construct the semi-classical microstates. By semi-classical microstate, I mean a microstate that has a valid semi-classical description. For simplicity in this talk, and Gautam, please feel free to ask me later about sort of more astrophysical kind of settings, which I can say things about. But for simplicity in this talk, it'll be easiest to talk about time reflection states, symmetric states in asymptotically ADS spaces. That's because basically, and we can do this in flat space also, etc. But because of the ADS CFT duality, for this audience, I hope to convince you that we really do know what we're doing. And you should believe me when I'm saying what I'm saying, because there's some dual field theory in which you would accept all of these calculations as being valid. In the flat space case, we would do the same calculations, but we don't have the dual field theory to guarantee to you that it's valid. So that's why I'm doing the ADS case for this audience. Okay. So we're also going to consider the eternal black hole, just because it's sort of technically all the formulae a little bit easier in the eternal case. You can similarly do with one-sided black holes, as I will mention later. And remember, the eternal black hole has a Penrose diagram like this. Here are the boundaries, here is past and future singularity, and here are the horizons. So remember that if I take a slice through this like that, an equal time slice, yeah? And by the way, I'm sorry about the lag between the image and my voice. It must be slightly unnerving. Anyway, if I take a slice like this, then the geometry, the spatial geometry in equal time slice looks like this. Here's asymptotic infinity. Here are the two horizons, and in between the two horizons, there is a wormhole. So equal time slices are Einstein-Rosen bridges between the two asymptotic regions. So the quote semi-classical microstates that we're going to talk about are going to look like this. So we're going to have, behind the horizon, we're going to have shells of matter moving around. We've chosen shells and spherically symmetric shells. As you can imagine, just for technical convenience, there's no particular reason why we have to pick spherical symmetry or anything like that. Anyway, but we'll pick spherically symmetric shells of matter that are moving around behind the horizon. And these things will have some inertial mass. Each shell will have some mass. Let's call it m. I'm going to call these things dust balls. And you can engineer these things, as you will see, such that the exterior geometry remains completely unchanged. In other words, the mass outside the horizon will remain the same, and you'll see how you can make such constructions in a little while. The back reaction of the shell is going to take the wormhole stretching between here, the Einstein-Rosen bridge, and kind of make it longer so that this bifurcation point kind of separates. So that's what the structure of these geometries will be. These are some new geometries that appeared in our work and Martin Sissietta's work. So I would like to think about these dust balls as highly atypical states, microstates of the black hole, highly atypical, which happen to be under semi-classical control. And we're going to use these to get an idea. I'm going to argue to you that these things form a basis, and then I'm going to calculate the dimension of the Hilbert space they span. That's going to be the plan. So how do you construct such states? So let's take some inspiration from the standard ADS-CFT dictionary. So in the standard ADS-CFT dictionary, if this is the eternal black hole, you know that the state dual to the eternal black hole, the state dual to the eternal black hole is supposed to be the thermofield double state in H left cross H right, where H left and H right are the Hilbert spaces on the two boundaries. So this is the TFD state, right, on the two sides. So usually both in the dual field theory as well as in the bulk, how are we supposed to prepare the state? Well, in the ADS boundary, the ADS boundary looks like a cylinder. Well, each of this point here, the circle here is really supposed to be a sphere, but so you start out with the Euclidean cylinder, you start out here and you evolve by beta over 2 in each direction and come up to t equals 0, and then you're supposed to cut the state there. That's the Euclidean state preparation algorithm, and will prepare for you in the dual field theory, the thermofield double state. The bulk version of this as well, you take the same Euclidean boundary, and then you sort of extend this into the bulk. And if you do that, you'll get this region here. This corresponds to this region here in the bulk, and it basically gives you the Euclidean black hole. Here's the horizon of the Euclidean black hole. Remember how I said it was a disk? And you do the bulk path integral so with these boundary conditions. You integrate up to t equals 0, you slice there, and then if you analytically continue, well, the horizon develops out of this Euclidean horizon, and that's what you're supposed to do. Okay? That's so you do the Euclidean evolution to t equals 0, and then you match to the Lorentzian geometry. That's the state preparation algorithm that we would say in ADS-CFT. Now, suppose I want to make an excited state. What do? So if I want to make an excited state, a different state, what you can do is you apply an operator at the Euclidean past, right? So here's the operator. Well, I'm actually going to make it a cloud, a spherically symmetric cloud of local operators. And then you evolve this way by some time, let's call it beta tilde r over 2, and you evolve it this way by some time, beta tilde l over 2. And what that will do is it'll prepare a state on the surface. And we can choose this operator O in the dual field theory to have a semi-classical dual. Right? We can make it a CFT state that we believe in ADS-CFT has a decent semi-classical bulk description. Okay. Basically, I can use it to create a spherical cloud of dust particles. Now, these are, this is an idea of doing this that goes back all the way to the beginning of ADS-CFT. Many people have done calculations like this, etc. In other words, if phi is in some operator of dimension delta phi, let's say delta phi is so the phi is some operator of dimension 1, then you can construct an operator O, which is a product of many such phi's, and the phi's are spherically distributed around the boundary in ADS. In other words, in the CFD. Then the dimension of the operator O will be like n times delta phi being the dimension of the operator phi, and n being the number of operators you put in. So you can pick delta phi of order 1, the dimension of phi of order 1, and we're going to pick the number of such phi's we put in to be of order 1 over g Newton. That is because we want to have a large shell which back reacts in the space, etc. In fact, most states will be like that. So we're going to take a very large number of such particles producing these back reacting shells. Okay, so this is supposed to be standard in ADS-CFT, HKLL prescription for states and all that kind of stuff. Okay, so as you'll see, I'm going to try step by step to basically do things that we consider standard in ADS-CFT. And I'm going to use that because in the end, the claim will be dramatic. So I'm going to try to keep all the methods completely standard, or as many of them as possible, completely standard. So what is the gravitational description of this process? Here's the past Euclidean boundary. This is the past boundary of that disk describing the Euclidean black hole.
Vijay, Hi, Vijay. Can I ask a question? Yeah. Yeah, if I could go back to the previous slide.
Sure.
Right. So, without ADS-CFT, I could have imagined considering, a large number of different species of what you call dust balls, and just by proliferating the species, I could make the dimension of the states that I make just arbitrarily large. Of course, in ADS-CFT, I can imagine that somehow the central charge of the matter in the boundary field theory is tied to the Newton constant, so you cannot do anything there, and presumably the
so Gautam, let me respond to you.
Yeah.
Let me respond to you.
Right.
So I will address this directly later. Okay. And actually, there's an easier argument than using the central charge, anything like that. We will directly show that all these states that you make using different species have a small overlap with each other, and that it's a gravity effect. The idea is, from the CFT point of view, if you like, the fusion, the OPE of any species that you make, the OPE of operators, contains a stress tensor. And because it contains a stress tensor, that is going to be enough to produce an overlap, a quantum overlap, not it's a small overlap between two shells made of any species. Basically, you can turn them into gravitons. The gravitons can talk to the other shell. So I will say more about this later. And if you could revisit then, that would be great.
Okay, thanks a lot.
So, okay, the lag is a little bit unnerving because I start talking and then the thing moves. Okay, so what's the gravity?
Here it is fine.
It's not lagging?
Yeah.
Oh, okay, so it's lagging on my screen. Okay.
Yeah.
So, so let's talk about the gravitational description of the same process. So here's the past Euclidean boundary. So this is the disk in which I've taken the past half. You insert the shell. So in the dual theory, this would be like this. I evolve this forward in time like that. And then we want to find a saddle point to solution. So we want to find a solution to the equation of motion, because strictly speaking, what I should be doing is the path integral going forward in time. But I want to write down, try to find out whether there's a saddle point in that path integral, a classical solution. So the saddle point would be a solution to general relativity plus a shell of dust, right? So what does that look like? The shell of dust has this character. There's some stress tensor built from some energy density and the velocity of the shell. And I'm going to think about this kind of solutions, right? These kinds of solutions, kind of semi-classical states. By that, what I mean is that underlying this, there's a real quantum state consisting of all these particles moving around, but it happens to be of a nature that I can visualize it semi-classically. So that semi-classical description will look like this. There's the left side and the right side of the shell, call it minus and plus side. If you work out the solution on either side, it will look like the solution for a Euclidean black hole. And then there'll be a shell that's moving around, and you can work out using the Israel junction conditions that the motion of the shell is controlled by some equation like this with some effective potential that you derive by talking about the Israel junction conditions and the rules of gravity. We're going to find infinitely many solutions of this kind. And all of these solutions have exactly the same exterior mass. Okay, so there are some constraints. We want the shell to be behind both horizons on this side and this side of the eternal black hole. And we need it to be behind the horizons because we don't want to change the mass, right? We want all of these things to be microstates of a black hole with the same mass. And if the shell fell in from outside the horizon, then obviously by Birkhoff's theorem, the mass inside and outside the shell will be different. So this has to sit behind the horizons the whole time. So the way you can do that, that imposes a constraint and goes like this. So here is a Euclidean disk describing, let's say, the right black hole. Here, right? So you want the shell, here's the Euclidean horizon, you want the shell to pass like this. And although the shell passes like this, I want to keep the mass of the whole system fixed, right? So what do? Suppose the trajectory of the shell dictates that you have an elapsed Euclidean time delta tau r. Then the amount, and then you agree that the amount of time on the right side here, Euclidean time here, is beta tilde r. We have the constraint that beta tilde r plus delta tau r, these two Euclidean times, must add up to the inverse temperature of the black hole as seen from the outside, and we hold this fixed. So this describes a shell trapped behind the horizon. And you do this similarly on the left side. So this thing is here, this is the left horizon, the right horizon. And the back reaction winds up stretching the wormhole in between them by a little bit. And if you do the Lorentzian continuation of this construction, so this is all explicit, right? You just write out all these equations. Then you have the shell comes up to t equals 0. You analytically continue to Lorentzian signature to see what it looks like as a state. And you'll find that there's a horizon, a shell behind it. So we want to think about these kinds of things as microstates of the eternal black hole that have a semi-classical description involving a shell behind two horizons. Okay. So let me make a comment. Suppose you wanted to work with asymptotically flat one-sided black holes, right? This is not yet collapse, but this is sort of more astrophysical in its character. You can do something very similar. You can show, and we did, that you could imagine, shells of matter, if you like, behind the horizon of the one-sided black hole. And if you look at what this, and you can solve for this, there are saddle points like this, there's infinitely many saddle points like this. And if you work out what these geometries look like, if you take an equal time slice, and look what it looks like. It basically looks like the usual black hole over here. And then when you get behind the shell, you have a smooth cap that looks like flat space. So these are very much the kind of geometries that Wheeler was talking about that were bags of gold. So the main reason why I'm not giving this talk with lambda equals 0 to this string theory audience is we don't have the dual CFT to build confidence, but other than that, every calculation we actually do in the bulk spacetime is basically identical. So for that reason, we believe that everything is valid there too. Let me summarize. Yeah.
So could you again, just maybe it was you said already.
Ayan, let me ask you, Ayan, before we continue with your question, let me ask you a question. I see that I'm like a little bit under 15 minutes to the end of the time. Is the end of the
there is nothing to worry about it. We can go. I mean, because as long as
because otherwise I have to stop taking questions right now because I should make some progress. Yeah. Okay. Please.
So no, just to understand the Lorentzian picture again of this setup. I mean, I understand this. You are setting up this. I mean, in rigorously we can set it up in the Euclidean state preparation point of view. But how do we define the path integral exactly? Are we doing it completely Euclidean, or when we are defining this path, when we are computing the number of states? Or so sorry, I did.
Yeah. So I'm going to treat the Euclidean path integral as a definition of the Lorentzian path integral. In any case, in the Lorentzian case, we never know how to do Lorentzian path integrals usually, because of all the problems with this, with the integrand oscillating and stuff like that. So the normal way I personally think about what a path integral is that imagine I've analytically continued to Euclidean signature where I know what I mean. That's just an analytical continuation trick. If I have to do an integral on the real line, I may do it on the complex, off on the complex plane, and then continue back. That's a standard thing in complex analysis. And I think of what we are doing when we do path integrals as being some infinite dimensional version of that. So here, the Euclidean path integral for me defines what the answers for the path integral should be. However, we would like to know what the associated states look like in Lorentzian signature. And I'm using the algorithm that we evolved to equal 0, we slice, and then we continue.
Okay.
This is what we would also do right? We would also do this even in, we don't even have to do this just in gravity. If suppose you want to discuss instantons and what instantons look like and why they look like tunneling amplitudes, if you look in Goldman's book, there'll be a similar kind of treatment, right? You do the evolution t equals 0, you slice, you continue, this kind of thing.
Yes, but my only confusion is rather is that so there are two pictures that you're giving. One picture is that you're using Euclidean path integral to prepare a state at some time slice, right? The other picture you're giving is to hold the time circle at the infinity fixed. So just a little. So exactly what is this? How you're?
So those two are not different from each other.
Yes.
So we are interested. We're interested in using the Euclidean path integral to prepare states with the property that the exterior geometry is fixed. Because I want to construct states that have a plausible interpretation as microstates of a particular exterior geometry. Because the idea here is, in the spirit of statistical physics, I've got to tell you what macro variables I keep fixed while computing all the micro configurations consistent with those macro variables. The macro variables that I seek to keep fixed here are the geometry outside the horizon, because that's what I take it to mean, that the exterior, this black hole is the geometry outside the horizon is fixed. So this condition, this constraint, is simply a constraint on constructing through the Euclidean path integral configurations that have the same exterior geometry, same temperature in the exterior geometry. Did that answer your question?
Yes. Okay, thank you.
Yeah, and the Lorentzian picture, you don't even have to look at it if you don't want to, right? My goal is to just use the Euclidean path integral to construct these states and then compute their overlaps, which we will do in a moment.
Okay.
Right? So we don't even have to look at this if we don't want to. But personally, if someone tells me I have a state, I like them to tell me at some point what does it actually look like with the Lorentzian time, and that's why we keep drawing these pictures.
Okay. And just maybe I'm asking ahead. I mean, in principle, you could compute the overlap between states also as an Euclidean path integral, right? Just to prove them, or
we are going to do that. That is exactly what we're going to do.
Thanks.
Yeah, we won't use the Lorentzian path integral. We use the Euclidean path integral to compute the overlaps.
Okay.
Yeah. So anyway, I've constructed these states. So I would like to talk a little bit about what we believe their meaning is. So what are our states like? I want to think about each of these things as a kind of quantum state. I'm going to call them psi m. M means the mass, the inertial mass of the state. As I've already argued, the inertial mass can, be take an infinite number of values. You can put you can put as many of these things as you want. It's not quite true. If you increase the density past some amount, eventually these things will be closer than Planck scale, the little particles, in which case you begin to worry whether you have control over them. But actually, you can get vast numbers of these things already well before you get to that kind of density. What's more, you can put 2 shells or 3 shells or 50 shells, and they can all move around. There's basically an infinite number of such states you can make. So one comment I would like to make about these states is I'm describing the description I gave a moment ago. So fundamentally in the CFT, I said, well, you apply all these operators, and that's the microstate. So that's good. But actually, then I also gave a description of the state as a semi-classical saddle point. So what does that mean? Well, a thing that's important to keep in mind is that if you take all of these dust particles and you move them by tiny Planck amounts, you're of course going to get the same semi-classical description. So you should regard our construction as we're giving one representative for each m. That is to say, we are the gravitational shells that we're going to use as a trick to do the calculation are a slightly coarsened gravitational description of the underlying microstate, which consists of operators applied at very specific positions on the boundary of ADS. Right? So, but there will be, of course, many such configurations that will have the same description as a gravitating shell once you've coarse-grained a little bit. Okay. So naively, these states that I've constructed span an infinite dimensional Hilbert space, and they're all feels like legitimate microstates of the black hole because the exterior geometry has stayed completely fixed. So I have now arrived at this bag of gold type problem. However, that's a little bit too quick because of course these states could have tiny quantum mechanical overlaps. So the next question is, the key question, is can we calculate the dimension of the space these states span? So let's do that. So once again, we have these dust ball states. They have many masses. I'm going to use this notation for them. And I want to compute the dimension of the spanned space. So we will do this as follows. We're going to use a standard linear algebra trick. And the standard linear algebra trick is as follows. One constructs the Gram matrix. The Gram matrix is the matrix of overlap psi I, psi j. So here's the Gram matrix, the diagonal elements of psi 1, psi 1, psi 2, psi 2, etc. Of diagonal elements are like psi 1, psi 2, psi 2, psi 3, etc. And in linear algebra, if I gave you a whole bunch of vectors, and then you constructed the matrix of overlaps of those vectors, then the dimension of the space those vectors span is the rank of this matrix G. Okay, so how do we compute that rank? The rank is the number of non-zero eigenvalues. So to calculate that, we're going to use an old trick from linear algebra, which personally I first became aware of from the matrix model literature in our field, but this is a basic linear algebra trick. What you do is you calculate the trace of the resolvent. Okay, so what's the resolvent? So you take this matrix G, which is the Gram matrix, and then you write out 1 over lambda times the identity minus the Gram matrix. That's called the resolvent matrix. And then you compute its trace. So you can show, and so now what I've done here is I've done a power series expansion of 1 over lambda I minus G. This is a geometric series, so here's the geometric series with some traces over there. So in this expression, omega here is the dimension of the Gram matrix, okay? So that's how many states are put into a bag. And there's a theorem, a statement, that the eigenvalue density of the Gram matrix of G is going to be the discontinuity across the real axis of the trace of the resolvent. So you basically take 1 over 2 pi I of the resolvent trace of the resolvent, evaluate at lambda minus I epsilon minus the resolvent at lambda plus I epsilon. And we're going to call that the density of eigenvalues. So the way we will compute the rank of the Gram matrix is we will take the dimension of the Gram matrix. Suppose I've taken n states to put in my bag, and I'm going to subtract from it the density of vanishing eigenvalues. And that object is going to give for me the rank, the dimension of the Hilbert space. Okay, so that's our plan. So what do we want to do? Okay, so I need to compute trace of powers of the Gram matrix. That's what this is, right? So, okay, so let's do that. Let's see what kinds of things we need to calculate. So we'll need to calculate the overlap psi m prime. We'll need to calculate psi m prime, psi m prime, psi m, and products of this kind, and so on and so forth, right? So, and in all of these calculations, one sort of little technical point of importance is that the first and last indices here will match because we're always taking traces. So those will match. That's kind of technically important later. Okay. So we are going to calculate all of these overlaps using the Euclidean gravitational path integral. So for example, suppose you want to compute psi m prime. What do? You prepare the state psi m via the path integral on the lower disk. You bring it up to here. Then you prepare the state psi m prime using the path integral of the upper disk, and you bring it up to here, up to t equals 0. Then you sew the path integrals at t equals 0, and you integrate. That's what you're supposed to do. So suppose you do that, and you try to do this in the semi-classical limit. Then what you're supposed to do is you do the path integral with the gravitational action. So you have the scalar fields, you have the whatever matter fields you have the metric. You do that calculation, and then you're supposed, if you want, and then because we're doing quantum gravity, what you're supposed to do is fix the boundary condition at infinity, and then sum over all topologies that you can use to fill in the bulk. That's the rule of how to do this. So we can sum over topologies, and okay, at the end of the day, you'll find a bunch of saddle points in principle. And so what you get to do is you fill in the boundary with all the possible classical solutions. Each of those gives you a saddle point contribution, and that's going to be the answer in the semi-classical limit for this overlap. Okay. So I am going to calculate this in the semi-classical approximation. As we've already said, we're going to use saddle point. So just to emphasize that we are doing an approximation of the full answer, I'm going to put this overbar on top of these calculations. That's just to keep reminding us that this is a semi-classical approximation of these overlaps. So let's do an example. Suppose you want to compute this overlap, psi m prime, and the diagram, given this disk boundary, the only thing you can fill this in is you just fill in the disk like that. And you see that when you try to do this, if the m and the m prime are not equal, there's no saddle point or classical solution that connects a shell of inertial mass m with the shell of inertial mass m prime. So this gives you a delta m prime. So now, in principle, there are quantum processes that allow splitting and joining and this, that, and the other that might change one shell into another. But this is going to involve exponentially many processes. And so it's going to be suppressed in e to the minus m prime, where m and m prime are the inertial masses of these shells. And so this is going to be suppressed by order 1 over g Newton. And what's more, because we have parametric control over which masses to pick, we're going to pick those masses parametrically to suppress any such quantum contribution relative to the additional contributions that we're about to compute. Okay. So basically, by suppressing that contribution, making dust balls of different inertial masses, sufficient different inertial masses, the dust ball states are pretty much orthogonal at this level. Okay. So this would appear to give a Gram matrix of a very large, essentially infinite rank, because if all of these states are orthogonal, then you have infinitely many states. But what about this quantity, right? The square of the amplitude, of the overlap. So now, well, so this is one boundary condition with an m and an m prime, right, for this overlap. And here's another boundary condition. So I'm calculating this overlap. And if I do that, then you have the first diagram, which is this disk with a shell kind of passing through, and here a shell passing through. And as already said, this will be proportional to delta m prime. So this is a diagram that's proportional to delta m prime, right? It's a delta function. The two shells have to be the same. But I already said that, or we've agreed for the moment, that in Euclidean, in the theory of gravity, the correct way to think about the path integral is you fix the boundary conditions at the edge of the universe, and then you fill in the boundary condition with all the topologies that are allowed in between. So in particular, what you're allowed to do, what you're supposed to do, is you're supposed to allow topology changing amplitudes. Well, that is actually a point that has been debated for decades in the field. And some people say yes, some people say no, some people say yes in some circumstances, but not other circumstances. But we're going to accept the idea that the gravity allows topology changing amplitudes. And so in this case, we're going to allow that there is this boundary condition, and if you fill it in with a different topology, that is to say, you can fill in the topology of a cylinder topology, where you have basically a wormhole, if you like, connecting these two asymptotic boundaries. Then there's this diagram, and now you can connect up the m with an m and an m prime with an m prime. So that's a connected wormhole contribution. And if you calculate what that gives you, it gives you this. So from you get a delta function coming from this disconnected, if you like, diagram. And from this connected diagram, you get something that looks like the Gibbons-Hawking partition sum of twice the temperature raised squared, and the Gibbons-Hawking partition sum raised to the power fourth. There's some details of this kind that come in. Okay, so this is for the square of the amplitude. Now, of course, we need to compute other things like the cube and the sixth power, etc. And I'm going to tell you that there are similar other diagrams you can calculate. And at the end of the day, the connected part gives you terms of this kind. And you get more and more terms of this kind for each term in the Gram matrix. So the net effect is as follows. So So now I want to pose a puzzle. The puzzle is as follows. We had found that this overlap, at least in the semi-classical limit, is delta m prime. So it vanishes if m doesn't equal m prime. But now we're saying that the square of the overlap is the delta function plus something else. So in other words, it's non-zero even if m is not equal to m prime. So the first question is, how is this even possible? So here's a proposal. So the proposal is that this is possible because the semi-classical Euclidean saddle points that we are calculating with are averaging over microstates that vary in tiny Planck scale details. In other words, remember, the same semi-classical saddle point is a description of many different microstates that differ in tiny Planck scale details. We already said that, right? If I change the positions of the dust particles by tiny amounts, you'll get the same semi-classical description. So suppose these states have the same macroscopic descriptions, but actually vary microscopically with sort of random phases. So for example, you could imagine that if you take the operator, the dust shell operator, sandwiched between true energy eigenstates of the system, then you would find some smooth part in that overlap, which is diagonal. It's a diagonal part that's smooth, and then you'll find some erratic phases. The idea here is that the theory of gravity is chaotic and therefore produces ETH-like amplitudes for simple operators. And so if that's the case, you will find that the expectation values of simple operators and energy eigenstates look like that. And then if you examine the consequence of that, it's going to have the effect that when you do things like compute the overlaps between such states, you'll get 0 unless A equals B. That's because the semi-classical calculation you're doing is averaging over those random phases. But if you take the square of it, that's because this A is equal to this A, you remember these indices match, it will happen that the random phases cancel in such a manner that you actually get a non-zero value. So the idea is that you're getting 0 here and non-zero here because the semi-classical approach is averaging over some microscopic. There is a true microstate that we're trying to calculate for, but there's some detail that's going to average out like that. Okay, so now we're going to count the microstates. So in other words, we have a whole series of calculations of this kind. Remember, we have the resolvent, we have the trace of the resolvent. That involves some power series built in terms of this gram matrix, the trace of the gram matrix to various powers. I already told you that the trace of the gram matrix to various powers, these are precisely the moments of the overlaps that I just described, right? It's hard to compute the powers of the overlaps. You can plug in the answer for what we got for these overlaps, these various kinds of Gibbons-Hawking type partition functions and everything, and work it out that you'll find a recursion relation. So this takes a little bit of work. You find a recursion relation of the following form, that the trace of the resolvent has this power series expansion where the coefficients involve these overlaps that we computed. So there's one more subtlety that we have to deal with. All along we've been working in the canonical ensemble. So in the canonical ensemble, a state has support on everything. That's because there's an e to the minus beta e, and then the e to the minus beta e, gives you support on every energy eigenstate. So what we really want to do, if we want to count entropy as the number of states in the Hilbert space, is count entropy that way as the number of states in the Hilbert space or the dimension of the Hilbert space. You need to work microcanonically, because otherwise, canonically, you have support in everything, right? Just suppressed support, exponentially suppressed support on very high energy things. So you need to project everything we did into the microcanonical window, and you can do this by this sort of Laplace transform, again, standard statistical physics trick. So we'll project everything we calculated into the microcanonical window, and then you can do the sum. So at the end of the day, after doing all of these calculations, which I won't repeat here, you get some equation for the trace of the resolvent that looks like this. So you have the square of R, of the trace of the resolvent. Here's a linear term. And then this is the dimension of the gram matrix. That depends upon how many states you put into your bag. And then S here is area over 4G Newton. Right? So I just wrote it as S because it's going to be the entropy later. So S is area over 4G Newton. That's what works out to be the case. And this is coming from the various factors of the partition sum that we're coming about.
Vijay?
So now you can work out from this. Let me just finish this one. I've come to the punchline, so let me finish punchline. So from this, you can compute the density of eigenvalues. So you get some smooth part, and then you get some part that's delta of lambda. So it's on 0. So this is the number of vanishing eigenvalues. So that turns out to have a theta function, omega minus e to the s, and then it's multiplied by omega minus e to the s. So what does this mean? If omega, which is the dimension of the gram matrix, namely the number of dust ball states you put into your bag, is less than e. So remember here, S is equal to, S is equal to area over 4G Newton is what we have here. So So, right? So if the number of states you've put into your bag is less than e to the s, turns out there are no vanishing eigenvalues because of the theta function. On the other hand, if omega is bigger than e to the s, there are omega minus e to the s vanishing eigenvalues. So you subtract out and you find out the rank of the Gram matrix, in this case, when you put enough states into your bag, is precisely e to the s, where s is equal to area over 4g Newton. So in other words, that is the entropy. Right? So that's so indeed the rank of G is the dimension of the Hilbert space. That's what we would call the entropy, and it turns out to be exactly equal to area over 4g Newton. Okay, so that's supposed to be the punchline. So let me say one more thing, Ayan, before I take your question. So this is trying to quickly address at the end of the talk another point that I'd like to argue to you that this is in fact a complete basis. The reason we would say that there's a complete basis is the products of any operator contain any other operator in a chaotic theory. And we've already invoked the idea that gravity is chaotic. Another way of thinking about this is, in our particular case, the products of any operator contain the graviton, right? And then so that means, well, strictly speaking, they contain T mu nu, I should have said. The products of any operator contain T mu nu, the stress tensor. And so this is equivalent to saying that the OPEs of any operator contain the graviton. And so because they contain the graviton, you have something universal. Once it's the graviton can change into anything else. Another way of saying what I have to say here is that suppose you gave me two dust shells made from different operators. So you pick operator O1 and you pick operator O2 and you make dust shells out of them. The overlaps that we would have computed are the same. The reason the overlaps are the same is it's a gravity thing. It has nothing to do with the particles of one kind changing into particles of the other kind directly. But the diagrams that involve, the instantons, if you like, that involve, the non-perturbative effects that involve just gravity, gravitational interactions between the shells, and that really doesn't care what the content of the shell is. So that's what makes it universal. So the bottom line that we would like to claim is that we have a universal accounting of black hole entropy in any theory which has general relativity as a low energy limit. So I have more comments, but let me pause to take questions because Ayan had a question and maybe Gautam has a question.
Go ahead.
So what I was asking was that so when you're doing the path integral, Euclidean path integral, when you're preparing the state, here you are seeing it as a genuine state that you have created and which has some departure in between. But when you're computing the path, now when you're computing this overlap using the same Euclidean path integral, you are thinking it's like an average. So, I mean, I understand this sentiment when people are just have purely Euclidean picture and like in the context of SYK and all. But now we are having.
So I wouldn't say that we're thinking about it as an average per se. We're thinking about the Euclidean path integral as computing a slightly coarsened version of the answer. Right. So, and that coarsened version of the answer will act as if the phases will cancel. It prepares the state, but the path integral prepares the state. But how am I actually calculating? I'm calculating using a saddle point, right? And that saddle point isn't the exact path integral. It's an approximation of the path integral. And so in what way does it approximate the path integral? It approximates the path integral by, it's clearly oblivious to these, to those phases that I mentioned.
So you're saying that although the leading order answer vanishes, it's just, but there is this random phases and which is actually there if you can manage to compute the path integral exactly. And then, okay, so it's, okay, I understand what you're saying.
Yeah,
so, but there's a part of the answer, and you're saying there's a part of the answer which is quite universal. That's the main claim. The part is that when you're computing this this double sum, the product of the overlaps, the square of the overlap, the forms
there you get
that is universal. That's the main claim.
Yeah, you get a phase. So at a technical level, the phases cancel because of the particular amplitude you're calculating, And so therefore you can calculate that and get the information out. And the point, by the way, of writing out the whole the Gram matrix and these powers and stuff like that is because the different so in a situation where you've got these kinds of random phases, a way to probe exactly what the overlaps are is to take all of these moments. So by looking at the different moments, you can get the detail out that you couldn't get with one of these objects. Like one of these things can average to zero or sum to zero, and the others, the moments, will carry the information that you were missing in that first calculation.
Okay, thanks.
Gautam?
Hi, Vijay. I mean, it looks fantastic. So at what stage did the Bekenstein-Hawking entropy enter your calculation?
Okay, so there are a series here of various kinds of overlap calculations, right?
Right.
Like this. I'm losing track. Over like this.
Mm-hmm.
Can you see this one?
Yeah.
So when you do this, because you're doing the Euclidean path integral,
Right.
at some point you're going to have things that look like e to the minus, integral r over the space, because the saddle point action will involve that.
Ah.
Right. And notice we're not taking any derivatives. There are no derivatives going on. So we don't have to worry about that conical defect issue or anything like that.
Yeah. I see.
Yeah, so these are supposed to be legitimate solutions to gravity throughout without taking that derivative. So you just write those things down.
You finally get exactly the subtraction of omega. This d of zero.
So let's talk about where the subtraction is coming from. It's coming from, suppose, so the whole, so what is the, let me write here. So I'm going to say rank of G.
Yes.
Is equal to the dimension of G minus number of zero eigenvalues.
Correct.
So we are going to calculate the number of zero eigenvalues, and so that's this thing. And so you see, if omega happens to be less than e to the s, you don't have any vanishing eigenvalues. These are all independent states. Well, they may have some overlaps, but they're not redundant. But if omega, the number of states you put into your dust balls you put into your bag, exceeds e to the s, then you start getting vanishing eigenvalues. And how many vanishing eigenvalues? It's omega minus e to the s.
So it's omega minus e to the, I see.
Yeah, exactly. And so you get e to the s.
I see. So this is the reason why it would work out also in flat space. That's what you basically want.
Absolutely. The calculation is almost identical in flat space. It's just that I will not be able to tell you all the words saying you must believe me because I put, these were just operators in the dual field theory, you've been doing that for 25 years, therefore all of that. I can't tell you any of that. But the bulk calculation is almost identical, right? The cosmological constant is sort of a little bit of an irrelevancy, right? There's add some piece, that's all. So I could give this, I've given some version of this talk where I only do flat space, but that's for a different audience who doesn't really care that there's some hideous dual. They just want to know what the calculation is in the bulk. But for our tribe, I think this adds confidence, that we have control, at least in that case. And then I'm going to assert to you the bulk calculation is identical. I mean, literally identical for the flat space case. So in all essential details. And so we have some confidence that will go through. Let me go through and sort of say some word about that, about really what you'd really like is to do collapsing black holes in flat space with one boundary. So what does that calculation look like? Okay, so this is the Penrose diagram of the collapsing black hole. Here's the matter shell that's collapsing from outside the horizon to make the black hole. So let me remind you, if I look on some equal time slice, here's sigma, what does that geometry look like? Well, on this geometry, you'll go from infinity and you'll come into the horizon and eventually it'll sort of cap off inside the horizon. Okay. So, okay, so now what does a microstate look like in our language? A microstate here could be like a small perturbation behind the horizon, something that's different, right? It's not just the shell falling in. Behind the horizon, there's something going on, right? So let's imagine that horizon, that excitation is like a shell, like one of our dust shells. So if you put a shell like this and you run it backward in time, actually you're going to get a past singularity, right? That'll be hidden behind the horizon. So any perturbation here will evolve backward to make a singularity. So you might say, well, then in that case, that isn't a microstate because look, there was no singularity back here. But actually, that is not true. This should be regarded as a microstate, the black hole. Here's why. Outside the horizon on this equal time slice, the geometry hasn't changed. So from the point of view of the outside observer, they have no idea if behind the horizon, this blue thing is there or not there. They can't tell. So it's equally a microstate. So because of this, you should think, so one way of thinking about what entropy is, what is entropy, right? At any given time, if I look at the gas inside this room, it is in some particular state, right? So what is the point of taking the logarithm of the possible states that this thing could have consistent with the macroscopic variables? The point is, if I am a coarse object or I don't observe all this details of the state, I'm a coarse object and I interact with the system will act as if all of these states are accessible, right? So basically, if I touch it, the reaction involves the gas molecules spreading out so they jump into a different state because I've pushed it. And the number of such states, the phase space of available states, is roughly speaking what the entropy is calculating. So the assertion here is that this is the way we should think about it. And in particular, if you tell me that, for example, the shell is very atypical, this can't be a sort of typical sort of microstate, I'll say that's fine. You should count all of those things as part of the entropy. For example, there is a microstate of the gas inside this room, which involves 5 minutes ago, all of the particles being in this one corner. That is a microstate that we add up as part of the entropy. It's included in the entropy, even though it's a highly, highly unlikely configuration, highly atypical, but it is part of the entropy. So atypical configurations are also part of the entropy. So our trick is to take highly atypical configurations for which we have very good control and then use that to construct a basis. Right? So next one is this. So our results also have a sort of rather radical and strange implication. So suppose I consider one of these microstates with a shell there. Oh, sorry, this is the original black hole with a horizon. Then I make one of these shells of matter. Then I make two shells of matter. I'm looking at an equal time slice in the time evolution. That's it. Then what will happen is that the interior geometry behind the horizon looks like this. There's a little bump there, 2 bumps, 3 bumps, etc. Essentially, the back reaction of the interior shells stretches the wormholes and increases the volume. So in this way, you can make wormholes of very big length, essentially infinite length, by putting many, many shells in, and the exterior geometries will stay the same. But our results imply that most of such states, the very long wormholes, are in fact superpositions of short wormholes, right? So a consequence of this is that volume cannot be a linear operator in quantum gravity, because if it were, if you write a long wormhole as a superposition of short wormholes and volume was a linear operator, then you can't get a big number out of the superposition of small numbers. Yes, that's a sort of interesting and macroscopic consequence, a macroscopic consequence of quantum mechanics, we would assert, whose meaning needs to be thought about. So let me, I have only 2 more slides, I'll finish with them. The first is concerns, you could say, is there some way of seeing that there are these microstates? So actually, our states have a sort of soft quantum hair. So if you construct, say, the left density matrix, right, there are 2 sides to the universe in these things. So from one asymptotic region, if I construct the density matrix, it has this form. It's not actually precisely thermal. And you can, even though, for example, if you take the expectation values of operators, like the mass of the state, you compute the expectation value of the Hamiltonian, you're going to get the correct macroscopic value. You're going to get the mass of the thing. But there are soft deviations in other observables. They're very, very infrared, and you have to pick the observables carefully. So this is something we're studying about, is there in some sense soft quantum hair that distinguishes the possible microstates. Not all of them will be easy to distinguish. So most of these effects are exponentially suppressed in the entropy, but it would be interesting to know if there are such deviations. That's something we're thinking about. So let me finish with one question. So besides the soft quantum hair, why can't we just detect all these states from far away? Why does there appear to be a horizon? So the answer that's also in progress is, and I have some paper with Onkar Parikar and Arjun Kar, Harshit Rajgaria from earlier this year that has some bearing on this, is that the idea is that at some level, all of the states we're constructing, by the time the time evolved to be deep inside the horizon, are extremely complex from the point of view of the asymptotic observer. So the reason why you can't measure these easily and why it acts as if semi-classically, as if there's a horizon, is that they're so complex that you can't measure them easily. So that's the notion. Anyway, I'm going to end there, and because I have run over.
Okay, so it's time for questions. So maybe I can start. So the volume operator you already know is, if it is on the complexity conjecture, it's not a linear operator, right?
Yeah, so the pertinent statement there is that if you believe the complexity conjecture, because my issues with the complexity conjecture are A, it's a conjecture, B, in those conjectures, usually words get said like volume equals complexity, and well, okay, I kind of think I know what volume means maybe, but I don't, usually the complexity part of that is not defined. So, okay. Now you might further respond, so since I've spent some amount of time thinking about what complexity would mean in quantum field theories, there are various definitions, like, you know, the Nielsen complexity, the Krylov complexity, etc. And it's true, they're all upper bound, because, well, you know, if you have a finite system, there's an upper bound to how complex things are. So if you take those words for granted, then there's some kind of bound, and yet the volume as naively measured keeps increasing without bound. So there's some statement there. I'm just, so all good as an intuition, but I think it's useful to actually have a precise calculation of some kind. On the bulk side, I think on the complexity side, it does get bounded because most reasonable notions of complexity get bounded. But then you'd like a detailed account, I think, of the bounding of the volume in the bulk. And there will be different approaches to that, and maybe this sheds some light.
But from the superposition, could you get some idea of computing some complexity, some in the bulk perspective, in some sense, that the fact that this long things are superposition of short things, and would you get some
yeah,
kind of...
so I think that's definitely an interesting thing to think about. So we made sort of slightly half-baked kind of approach to that in our paper, which involves saying, well, you have one shell. Let's suppose the one shell can split and transition to two shells, and then transition to three shells, etc. And then we made some argument about how the complexity of that, in the sense of Krylov complexity, would grow, and how that's related to the effective bounding of this volume. So that's a sort of a toy model kind of approach. You're really asking in some, can you just sort of agree that here's the quantity that computes the volume? I think that's what you're saying. Correct me if I'm wrong. Here's an object that actually measures volume, and then you calculate the volume, and you see how that changes in these states. As they get bigger, you take the very big wormholes, and then you say that this is the superposition that they're equal to, and then calculate and see what happens. I think that's what you're saying. Correct me if I'm wrong. So we haven't done that. It'd be interesting to try to do.
Thanks, Vijay. Actually, there is a PhD student who wants to ask a question, but is a little afraid. Maybe Nehal, you can just simply ask. Why not? And just,
yeah, you should ask the question.
Please just ask. I think it's easier rather than read your question. On
yeah, you should ask the question, and you should turn on your video.
Where is he?
There's a problem with his. Was that?
Yeah, it seems, Nehal, there's a problem with his audio. Maybe I read out the question then. Is it obvious? Yeah, is it obvious that the Israel junction conditions with the shell hold during the Lorentzian continuation while making sure that the mass doesn't change outside the horizon. Intuitively, I would like to think that one needs to make sure this holds at all times, not just at t is equal to 0 Cauchy space.
Okay, so multiple answers to that question. First of all, as far as the overlap calculations we're doing, we just need the Euclidean solution and up to t equals 0, and then we overlap the other one. So it's actually totally fine to do the Euclidean calculation up to t equals 0. But in terms of the Lorentzian continuation, yes, the Israeli junction conditions in this case do hold in the Lorentzian case. So we've checked that. And another way of saying this is we could have, instead of trying to do this calculating in the Euclidean section, then take the Lorentzian continuation, you can just start in the Lorentzian section and write down an ansatz for a solution which involves a shell moving behind a horizon which is stretched out, solve the Israel junction conditions, and you will find the solution that advertises. So that should be fine. I hope that answered your question.
Okay. So if there are no further questions.
Maybe I can just ask one more to Vijay. So, I would have expected that you would encounter some divergences in your calculation of, the things like the dimension and the rank and so on, because you were talking about, I presume that your omega, which is the dimension of the Hilbert space, is some infinite stuff. And presumably you're using some regularization, which is also the same regularization that you were using in computing the other one, which gives you the number of 0 eigenvalues. And so that the cancellation between the two factors of omega is, is it a little bit?
So may I comment?
Yeah.
So may I comment? So to avoid having to do that, we go the other way. We start with 1 dust ball, all good. 2 dust balls is all good. And we keep counting. We get to e to the s plus 1 dust ball, and what do you know? It turns out you only have e to the s independent states. Then we take omega equals e to the s plus 2. Basically, we start small and make it bigger. So the calculation is finite everywhere. And then, of course, you say, well, if you take the infinite limit, is there some problem with the limit? Well, that I obviously can't guarantee 100%. But for every finite amount of dust balls you put in your bag, it will be this way. And then I've already argued that that's a basis. So hopefully that's fine.
Okay, thank you. I got it. Ion, you are muted.
Yes. So, okay, if there are no further questions, we can formally close this, but we can informally continue.